Okay, cool. All right, hi everybody. I'm excited to be here and talk about performance measurement. My name is Daniel Spoonhauer. That's what I have published under, although these days almost everybody calls me Spoons. And I hope in this session that I can convince you that when you think about performance, especially for complex systems, that you can't just do that in terms of a single number, but as something a little bit more rich. And I'm going to kind of build up a bunch of examples around that. So just quickly about me. I studied at Cornell and at CMU. When I was at CMU, I did a bunch of work on garbage collection implementation and on the implementation of parallel functional programming languages. And then as a programmer, how you can think about performance when those two things kind of combine. I spent a while at Google building infrastructure there. And now at Let's Step, I'm the CTO and one of the co-founders, where we build tools for measuring performance in distributed systems. I think the thread in all this for me is like thinking about and building tools, whether they're sort of conceptual or not, for helping programmers to understand performance in those systems. So the story I want to tell goes back a long, long time, but I sort of want to start here, which this is the Twitter fail whale. Everybody, I hope, recognizes it, or maybe I'm just dating myself. But the idea was what happened if you went to Twitter maybe 5 or 10 years ago and the site was overloaded. This is what you'd see instead of tweets. And the problem was not just that they needed like a bigger machine or more RAM or something like that, but the people that were responsible for keeping the site up fundamentally didn't understand it, and couldn't understand what was happening and what the problems were. They had a lot of monitoring in place, and that didn't help them. And so they, I think, and as far as I understand anyway, invented a new word, observability, to talk about not just the idea that you have some measurements about your system, but that you can have not a system that's designed and built and the tools around it to actually observe it and understand what's happening there. This is sort of a rough outline that kind of ends with observability, or I guess it's kind of a thread in the whole thing. But first I want to talk about how we understand what's going on, what kinds of things we measure, then how we understand why those things are happening, and then I guess the thing that I sort of want all of you hopefully to keep in mind is first kind of thinking as a programmer, what are the kinds of things that you would want to know? And then as folks that are designing and implementing frameworks and languages and things like that, how can we provide tools to programmers to better understand that kind of performance? So let's see. This just kind of sets some context for things. So when I talk about performance, I'm going to really focus on latency. That is, how long does it take to service a request or complete a transaction. These are really old things, but just to kind of to set the stage in a way, which is, so Google did this experiment, I think a little bit accidentally, that showed that when they increased the time it took to render a page by half a second, that resulted in 20% fewer searches. Around the same time, Amazon did a study and that showed that even 100 milliseconds of latency caused a 1% drop in sales. And then at Yahoo, a couple of years later, they did some work that showed that 400-second increase in the page rendering time actually increased the number of users that clicked back before the page even rendered, or they just got bored apparently and thought that something wasn't working. So back then we were talking about rendering HTML, but the user experience today is based, we're not talking about just like loading a page maybe anymore. It's maybe requesting a ride on Uber or Lyft, or looking at your newsfeed or something like that. And the implementation of those things has changed a lot in the last 10 or so years, from something that might have been a little bit simpler to a much more complicated system. But fundamentally, we're sort of still talking about the same metric. We're still optimizing for the same thing. So what's happening in the system? How do we measure the performance is experienced by users, and then how do we measure what's happening internally? So I'm going to kind of walk through the history of this a little bit. So if you kind of go back to 2002 or so, you were building an app. You wouldn't have called it a monolith then, but today that's the kind of word that people throw around a lot to describe what was probably like a big JVM or something like that, maybe a big C++ process, running on a server that you probably like put into a rack somewhere. And what you measured was the average latency, the average response time. I'm going to show a bunch of time series like this where time goes across the bottom from the left to the right. So now it's going to be over on the right. And here well, this is pretty boring, it'll get more interesting later. But this is showing that the average response time, not only is it totally flat over the, whatever this history is, but it's also about a millisecond, so quite fast. So that's good, it'll get more interesting later. The reason why we can use average latency is that we're assuming that the distribution of them is normal, roughly. So the average is actually a pretty good stand-in for the overall population. And sort of the assumption is that if there were to be a problem in performance in some way, that would show up in the average latency. So we would notice it, we could do something about it, we could fix it. If you kind of go forward maybe a decade or so, now maybe your application looks a little bit like this. So again, you started to have some big thing in the middle, still might be a JVM, now you're running maybe Ruby. I can't remember if this is a Ruby time or not yet. And that's running not on bare metal, but maybe on AWS. And you're talking to a bunch of managed services. So your big monolith's kind of on top, and then you've got these managed services, and those in turn are implemented in a kind of distributed way, and will fan out across a bunch of different servers. And any given request isn't needed. All of them, sort of the yellow ones that are highlighted here, are sort of examples of what might be part of a particular request that you're serving. If you kind of squint, this is actually also what Google Web Search looks like. When you do a search, that gets fanned out to a million processes, each one of them searching some part of the web or whatever documents that for what you're looking for, and then the results kind of filter back up the tree. So when thinking about response latency, the naive thing is to say, well, let's just look at the average of all of those dependent services. Of course, that's the naive approach. It's not going to work because you actually need all of those results in order to serve, at least in the way most of these things are implemented, all those results in order to serve the result back to the user. So you're going to have to wait for the last one. So it's not the average, it's actually the worst case that you're interested in now. And so what that meant was that we're going to start looking at higher percentile latencies, right? So just to make a super concrete example, say that we look at one of these little orange, yellowish servers down at the bottom, and say that its average latency was 1 millisecond, so still quite fast, but that 1% of the requests took more than a second. If you only depend on one of those servers, you're fine. So again, that will just basically bubble up, so 1% of your requests will also take more than a second. But as you have a wider fan out, and also as the stack gets deeper, that problem is going to compound. So if you depend on 100 services below you, now 63% of your requests are going to take more than a second. So what was pretty rare is suddenly becoming more and more common. I think kind of obviously just due to the fact that you're kind of multiplying all these things together. So this is the part where I feel like I should have taken more probability in statistics as an undergrad, but anyway, here I am now. Right, so now when we measure something like 99th percentile latency, again, sort of for the same service, it's a lot more interesting, it's a lot higher on the graph. You can see some blips that are happening over there, some other shifts that are sort of happening. And now the idea is if I want to try and predict some problems that are going to happen or recognize when a problem is happening, if I'm looking at 99th percentile latency, that's going to let me get ahead of that and react in a kind of appropriate way. So just kind of looking at the overall picture, we're still sort of assuming that the distribution has sort of one big lump in a way. Maybe we're being a little bit more realistic about the shape of that curve, and we're looking at what's over on the right-hand side of it, and we're going to track these percentiles over time. Hopefully that's not super hard to get, but like the percentiles are definitely going to give us a better picture. One thing that's kind of interesting from implementing this and from a tooling point of view is, of course, whenever we're talking about like gathering data from just one server or one VM, we're gathering it from a bunch of different places. So if we're gathering average from a whole bunch of different services, it's actually pretty easy to combine those. Just if you want to do the weighting right, like there's no problem there. And that's why a lot of tools have actually continued to focus on average, or one reason why a lot of tools continue to focus on average is the way of measuring this thing. It's a lot harder to combine 99th percentiles. Like there's no way of just taking 99th percentile from over here and 99th percentile over there and like, I don't know what you would do. Anything you do is not a real number. You can't average them, you can't, there's no weighting that you can apply, anything like that. Like you're just gonna get a number out, but it's not gonna be representative of any of the sort of populations. So that's one thing to kind of think about, but if we continue going forward, so back up now to the present day, so now at least in our business we see a lot of different architectures. A lot of them look a little bit like this. So A lot of the customers that we work with still have some monolithic piece of their application, but they've started breaking it off into all these little smaller services or microservices, where the idea, each one of those things can be sort of independently built and deployed and scaled. And there's a lot of nice things about that. One thing it does, though, is it introduces a lot of complexity into the system. And so, we can measure 99th percentile, but that is really assuming that there's sort of one behavior that's interesting about the system overall. And that's not really the case. So I think to kind of try to illustrate this, what I did is I looked at a bunch of, to look a little bit deeper, we can look at histograms. And so I grabbed a bunch of histograms describing the performance of a bunch of different parts of our software. And I just tried to kind of pick them randomly. I was actually looking for one that was kind of normal, but I never ended up finding one. They all kind of look like this. So just a quick reminder. So in contrast to the latency graphs that I was showing a second ago, the histograms are showing latency on the x-axis. So now, whereas lower was better, further to the left is better on this. And then the y-axis, of course, is just showing the frequency of those things, right? So on the bottom left, this is kind of typical or kind of nicer looking one, which is like, well, you have a big cluster of stuff over on the left that's pretty fast, and then it kind of trails off, and you've got a few blips kind of out on the right. But I think the one up on the upper left is pretty interesting in that you have these two distinct populations that are totally separated. So a lot of the requests are handled in, it looks like, less than a millisecond, but there's a whole chunk of them that actually take more than 100 milliseconds. And if you were just looking at average latency, well, that's not representative of any of them. That's somewhere in the middle, probably. And even if you were looking at 99th percentile latency or any high percentile latency, you're going to miss out on the fact that there's really two distinct things that are happening here. So to kind of go back so like looking at over time, we can see like this is an example of something in our servers. I'm going to try to use this as kind of a running example, but the average latency is pretty fast and pretty consistent over time. It's about 500 milliseconds. But there's this kind of blip that happens over here, where it took almost 18 seconds to render this page. And that's the example we're going to dig into a bunch kind of over the next couple of minutes. So yeah, I guess the question is, as a programmer here, like how worried should I be? Like, is there something interesting happening there, or is this just sort of, it's going to happen once in a while and that's fine? So one thing we can do is by looking at the histogram, we can see, in this case, actually, there's a bunch of different behaviors happening here. So there's actually sort of 4 clusters of behavior that we could look at independently, try to understand what's going on there. So just to kind of come back to this, like in an application that you're building as a true distributed system, just measuring a single value like 99th percentile is not going to be enough. Measuring something like a histogram is going to be really important. One thing you might ask is, could we just use more time series? Like, are we just not measuring enough things, right? Maybe we just need more of what we had. And the answer, which this super scientific graph is trying to convey, is no, not really. So the thing is, if you think about sort of the state space of an individual service or all the different behaviors that it could exhibit, like that's fine, that's one set of things. Now you've got a second service that has its own, and a third and a fourth and a fifth, but now you need to kind of consider all of the different interdependencies of these things and how those different states might relate to each other. And so as a whole, the number of different behaviors of the system is going to grow combinatorially with the number of services that you have. So in the end, you're not going to be able to do that, and I'll talk a bit in a minute about some other ways that kind of doesn't do so well. But one thing you might ask is like, well, we did lose something when we went to histograms, right? Like we kind of lost the ability to see these things over time, right? Which was something that was pretty nice about the time series. And this is something actually where there's a lot of work to be done. I think it's some interesting possibilities here. So one option is to do something called a joy plot, which is named after this 1979 Joy Division album. The data actually comes from some astronomy, but they stole it, and that's what people call it now. Sometimes they're called ridgeline plots as well. But the idea is you take the histograms and you sort of stack them up one behind the other, so that time sort of goes back across the set of ridges. And now you can actually compare both, across the entire population, understand these different modes, the different behaviors, and understand how it might be changing over time. So the one on the left here, the black and white one, is again something taken from our service. You can see there's a big lump of relatively fast ones, and then there's some sort of shifting behavior over on the longer tail that seems to be changing a little bit over time. Real scientists also use these things occasionally. This one shows changing global temperature patterns over time. So I guess I hope it should be pretty obvious. I'm not trying to sell anything too hard, but that percentiles are better than averages, and that histograms are even better than percentiles. There's a couple of other things, though, that are important in understanding what's happening. So even if I just go back to a simple time series, the goal in trying to understand what's happening is often about trying to explain the variation. And so here we had some jump in latency that eventually came back down. And one thing that we might want to do is break that down into some components in some way, break it down across some dimension. So in this case, if I break that one metric down across different machines, you can see that there's one machine here that actually explains all of the variation that we saw in that one. So now if I'm trying to debug the situation, I can focus on that one machine. I can try to understand whether it's misconfigured, having some sort of problems, or just overloaded in some way. This idea of breaking down data in the number of different values is sometimes called cardinality lately, which is a true term, but it always sounds super jargony to me. But it's just the number of different values across each dimension, sort of cross-product altogether. And the problem is, like, for something like the machine ID, where the cardinality is the number of machines, which is probably pretty small. Some of these dimensions can get bigger. So one example that could be bigger is the number of users in your system. This is pretty valuable for us. So this is another histogram from our system. You can see there's a couple of different sort of behaviors happening here. This is part of our ingestion pipeline. So this is basically on the critical path for us to get data about our customers. And one thing I did was to try to understand this a bit better is to start to do filtering by different customers. So I grabbed and filtered by one of our bigger customers. And that customer, it turns out, is responsible for a lot of that big lump over on the right-hand side, which is kind of a bummer. As a big customer, they're important to us, and they're getting kind of the worst behavior. And just to kind of double check, I also looked at a smaller customer who's getting a totally different kind of behavior out of this. A lot better, as it turns out. So great, so maybe that's something I should look at, that sort of dimension is valuable in a way. The problem is that user ID might be, we have thousands or, hopefully someday millions of these things. And once the cardinality gets beyond a few hundred, it either gets really expensive to store the data, or you have to start sampling in a way that you lose a lot of fidelity around it. Sort of an extreme example of this is we have, saw in some of our data a customer who tagged their the instrumentation with the deadline, the timestamp deadline of the request. So each request had this deadline, they stamped it, and obviously, I think anyway, it's not that relevant for doing this kind of analysis, but it was useful for something else. But there's obviously a lot of different timestamps that could be there. So in implementing a system like this, it's important to be able to understand what the dimensionality of these different things, of each of them would be, so that you can sort of correctly process the data. Because if we try to keep independent time series for each of the different deadlines, that would just obviously be sort of an insane amount of data. I guess kind of looking back at how we measure things and trying to think about like what would make a good tool or not a good tool. So the precision of what we can describe and sort of the fidelity is pretty important. The limits that we have in terms of the cardinality is important. Just in general, the amount of like the volume and sampling, sort of the more volume and the less sampling that we can do, the better. So we did an experiment where we thought, maybe we could save a bit in terms of costs if we reduce the number of buckets in our histograms. So if we can go from 400 down to, or from 200 down to 40. And when you do that, at least this is sort of a typical example, like it ends up being pretty flat in the sense. So there's not conveying a lot of information anymore. Yeah, so in this case, more information is better. Another thing that's pretty important is understanding how quickly the data is going to appear, how fresh is it. So if you think of sort of where we are in time right now and what you have available in your performance measurement system, there's some delay between when an event happened and when you can see it. And in the system that we built at Google to do tracing, Google's internal system called Dapper, For some of the workflows, there was like a complicated analysis that had to happen, and that freshness was like several hours, which would be fine if you're doing some sort of optimization, but if you're trying to use this data to respond to an incident or to see if you're trying to maybe mitigate a problem and you want to know if it's been fixed, ideally, you get this something on the order of tens of seconds, maybe even a little bit faster. The other thing that you would want to know is how long the data are kept for. So it might be useful to look at data from a couple weeks ago, maybe even a couple months ago, and be able to compare that with what you have now. Probably not too much beyond a couple of months, and certainly probably not a year ago, just because the software has probably changed a lot and your users have changed a lot too. And all these things, I guess the theme of this is more data is better, right? The more data we have, sort of the better measurement we have, which is either more precise or allows us to understand it across more dimensions, or we can see it over a longer range of time. In contrast to that, as we switch to the kind of second part of this and trying to understand why things are happening, less data is actually going to be important. And so I want to kind of walk through some examples of that and go back to this thing where I was trying to debug this page load. So when I was showing the histogram before, remember there were a bunch of these different clusters in the histogram. So what I wanted to do is sort of dig in and understand what was happening there. Why were these ones slower? What made them different? So kind of the typical kind of workflow in this is a sort of iterative process. You look at metrics, you kind of go spot check some logs or some traces, and then you sort of hope that you find something that helps you figure it out, and that you have some sort of aha moment where you discover what happened. Unfortunately, that doesn't always work out so well, and so a lot of times you sort of end up sort of staring at this graph again, and then and thinking about it, and I often hear something like this at times where it's like, oh, maybe it was just a networking blip. That can explain a lot of problems. Could have been the garbage collector. That happens at times. Sometimes something a little bit more vague, like it was just a one-time thing. And if you sort of step back from all of these, like at some level, what all of these things are saying is like, it was magic.
Not my fault.
Not my fault, maybe. Like, there's no way I could have predicted that. It'll probably never happen again. Even if it's going to happen again, there's probably no way I could prevent it. And I think if you take one thing away from this talk, like remember that at scale, these things will always happen again. And it's probably not any of those things. So keep an ear for when you hear that yourself, or when maybe when you think about maybe saying it yourself. So again, one thing is maybe we just need more metrics, like maybe we're not measuring the right stuff. This is just sort of a sample of metrics from one of our dashboards from an incident that we had last year. And obviously something is going wrong, something's happening here. But the trick is understanding why. So there's sort of two problems. One is that there's a lot of correlated failures, so the same problem is going to show up in many different places. At least in the organizations I've worked in, the chances are that there's between 0 and 1 people that can look at this and tell you what the actual problem was. The other thing that's a little bit not so good about more metrics is that it sort of exacerbates this problem about magic, in the sense that, like, if you created this dashboard and a bunch of really smart people sat down and sort of enumerated all of the things that they thought could go wrong, if I come into that and say, like, well, none of those things explain the problem that I'm seeing, and they're all smart, they thought of everything can go wrong, it must not be a thing that we should really be able to try to predict. And so I think the takeaway in this is, like, more what is not necessarily the same as understanding why something is happening, and in fact, often explaining why involves getting less data than getting more. That is reducing the search space. So just to borrow a little bit of terminology from medicine, and I think there's a lot of sort of apt things about this comparison. So a symptom is what you measure to begin and sort of continue sort of investigation, and then a diagnosis is when you identify that problem. And there's a guideline among folks that run these big distributed systems at places like Google, which is that you should alert on symptoms rather than causes. And I think back to that sort of the medicine analogy, like, I don't know a lot about medicine, but I know that if my 3-year-old has a high temperature, that I should do something about that, right? And the thing that's great about in medicine about body temperature is that it's really cheap to measure. It's really easy to measure. Like, it's not invasive in any way, and that it's quite comprehensive in terms of the kinds of problems that it can indicate, right? So, and the same thing is true, we should be thinking about what are the kinds of things that are easy to measure, that is, symptoms that are easy to measure that are indicative of that there might be a problem, without necessarily worrying yet about what the actual problem is. And I think to go back to sort of this concrete case, like here what really matters is the latency that the users are observing from the outside. We can measure latency all throughout the system, but really latency further down the stack is only important in as much as it can help you understand latency higher up the stack. Right? And so recognizing that it's sort of secondary and explaining that is important in what's going on. Cool. So sort of back to my problem here. Why is this happening? So I'm going to sort of continue to build theories here and try to, I guess, try to validate those in some way. And as a tool builder, I guess I see our job is to provide evidence to the user to either validate or falsify these theories. So the first theory I kind of want to test is this slowness due to errors in some way? One thing I can do is I can go look and see what other errors are occurring, right? So it turns out that there are a lot of errors occurring right now. Cool, maybe that's the problem. But before I kind of get too deep into that, what I should really do is look with a little bit more context, right? So if I can compare to what was happening an hour ago or a day ago or a week ago, it turns out that there have been errors occurring for a long time, the same kind of errors in roughly the same distribution for a while. And so that's pretty important because in these complicated systems, like there's always going to be weird things. There's always going to be things that are broken. And in the course of, I'm trying to fix what I think is a real problem, I'm never going to be able to solve all of those other problems, and I shouldn't because most of them apparently don't matter at all, right? They're just other things that are there, they're noise that's in the background. And so, yeah, what's important here is that I've been able to sort of eliminate this as one possible cause in what's going on. So I guess the next thing is like, what actually took 18 seconds? Like, can I figure out like what was the thing that did that? So the tool I kind of want to use to do that is a tracing tool, and so kind of just a brief introduction on that for those that don't know. So here's this distributed system that I showed before, and I think everyone's familiar with the idea that there's some logging that we have, some logs in each of these servers that I can go look at. And the idea of a trace is I somehow want to go find all of the different information that's relevant to a particular request and gather all that together and kind of tie it into a single trace. So often a trace has this kind of like tree-like structure to it. That might be logging information that can pull together metrics, other timing information, other metadata, and kind of put that all in one place so I can sort of understand what happened end to end. There was a really nice talk that Lita Cho gave at Strange Loop this year, kind of going into a ton of depth on this and what you can do with tracing. That's pretty cool. But I just want to show a couple examples about how I use them in this particular example. So here's sort of one visualization of a trace for this slow request. So traces you can kind of read a little bit like Gantt charts. So time goes across, and then down is sort of going down the stack. And so each sort of color on this represents a different service that we're traversing in the course of doing this. And then each bar is a single sort of operation. You can think of that as like one RPC call, usually not quite at the granularity of a function, but something a little bit higher level. And then the width is how long that thing took, right? So in doing this, like this particular trace had 400 something different components to it, so there's still a lot of information here. And really the tool that I want to use here to help narrow the search is the critical path, right? So trying to understand, how to make this thing faster, like if something's not just looking at what took the slowest part, but what was the slowest part that was actually on the critical path, kind of by definition is what matters. What it turns out, sort of surprisingly, was that we were blocked on actually listing objects in an object store. Like maybe the more obvious thing would have been actually reading the data, but that turns out to be like way off the screen here somewhere in a part that didn't really matter that much. And so, great, we've identified sort of the root cause, at least we think we have, and so we can optimize the way that we list these things, deploy a new version of this service, and then go back and see how we've done in terms of performance. So things got a little better, like here's our blip from before, but it's still not as good as I'd like it to be. In fact, there's still sort of a 12-second request here. so that's pretty long. So let's keep digging a little bit further. Let's go back and kind of look at this histogram and see if I can kind of zoom in on one of these clusters. So the thing that I would really like to know is like what makes that cluster different. And unfortunately, I don't know of actually a tool that'll do this for me automatically today. It would be really cool, but what I ended up doing is just comparing kind of by hand a bunch of those requests against other requests and see if I could sort of eyeball differences between them. And one thing that popped out really quickly was that the slow ones were actually from one of our bigger customers. Maybe this isn't surprising to other people. It was sort of surprising to me, like in the same way that we draw these kind of long tail distributions for latency, we can draw that same thing for our users a lot of the time, especially in an environment where you're serving other businesses, maybe a little bit less so in a consumer, for a consumer product. But in a place where you're serving other businesses, you'll almost always have bigger customers, and then bigger customers, therefore, they pay you more, they're a bigger portion of your revenue, and often they have a bigger, harder workload. So they're getting actually the worst performance, which seems sort of, I don't know, wrong in some way to me. I was working on a project at Google, which sounds really trivial in some ways. We were working on the API endpoint that served the list of projects that you had in Google Cloud. So it would just, and it turned out to be really important because that, for whatever reason, was on the critical path for rendering the UI. And so we had a team that was like focused on improving that. And I had a conversation with some senior manager about it, and they were, they got it, like, this is important to the experience. They understand, based upon all that stuff I was showing you before, about how latency is really important to user experience. And they said, well, wow, how many projects do most people have? I said, well, most people have one. Most people have one project. And he was kind of like, how much time are you spending optimizing this thing? I was like, oh, no. I mean, the people that pay us have a lot, but most people don't pay us. And so what we're really doing is optimizing for this tiny selection of users where performance is really different, and it turns out also really important. So in this case, yeah, so I recognize it was an important customer, and that's good because I might have written this off as just like a networking blip or a garbage collection or something like that. And what I'm actually doing is actually improving the experience for someone that's going to be important to our business. The other thing is that these customers are often sort of a leading indicator, in that we want there to be more customers that grow to that size. So if I'm fixing this now, then I'm actually fixing it for a lot of people in the future. Okay, so I dug in here. And then it's probably a little bit hard to read, but the thing that turned out is that this was in now the decompressing and unmarshalling of the data that we're reading back from the object store. So roughly like reading it out of some data structure. And then sure, we can go optimize that. It's actually not totally clear that it was my fault in writing this code or whatever. In that, it might have been something else that was running on the machine at the same time. So there's a little bit of the story still to tell in some way that I'm not going to tell here. I gave a talk last year where I sort of described how you could build a tool to actually discover this kind of thing, because on one hand, it might be my fault. I might have written bad code, or maybe I over-parallelized my own code and I was contending with myself. But it could have been some totally different request path that was actually using these resources. In this case, it was CPU. It might be contention for a lock or a shared table or something like that. And there's sort of like, I think, a theme in this discovery of why something has gone wrong, in that we sort of alternate between this zooming in and zooming out, right? So I started from a very high level. I want to see an overall picture. I'm going to zoom in now to a particular cluster of requests. Maybe look back out and how that compares with things in history, what's changed over time, and now zoom back in and look at a particular request. Here I'm at that request, but maybe I actually need to zoom out again. I need to look at a bigger picture to understand what's going on. And so I think, in trying to answer why and in assessing how well our tools are doing that, really there's a couple of things that we can look at. One is, do we have the right context? Is that historical context? Another kind of context might just be just general frequency analysis of some of the different metadata. How frequent is a particular tag? Is that interesting or different or new? Looking at, of course, at the critical path, which operations actually mattered. This kind of correlation, I think, in particular, just-in-time correlation. Like, I didn't know in advance that I would want to necessarily correlate with what was happening for a particular customer or a particular machine. But being able to do that sort of exploration in real time was really valuable in this case. In this case, maybe contention could be helpful. I didn't talk at all, but There's also the idea that you would want to understand like what error is further down the stack, and even I think some interesting work in using observations from throughout a distributed system to try and determine which pieces of it are failing, which is pretty cool. So again, all of those things are about reducing the amount of data that I as a human being have to look at. Just because the search space is so big, I'll never find the answer if I'm left to do it by myself. Okay, so then kind of just like thinking overall about where we're at, sort of classically when people think about observability, they look and they say, well, you know, Google, Facebook, Twitter, like they have metrics tools, they built logging tools, and they built distributed tracing tools. So like if we do those things, then we'll be set too, right? Like that's what we need. And at least in my experience talking to a lot of people building systems, they have all of these things and they're still sort of in the dark. They're still not sure about how they can explain the problems that they're seeing in their systems. And I think the sort of fallacy is that these are just data sources, right? These are just different kinds of data. And what's more important is to sort of flip it around and look at like, what are the things that I want to do with that data? What are the activities that I want to do? And this sort of, I think, was what I was trying to reflect in this talk, is that we should be thinking about measuring these symptoms and getting the right data to do that. And then having the right tools to refine the search space and answer why things are happening. Just to kind of now think about what our tools are doing, like are our tools giving us the right kind of precision that we need? Are they providing the right sort of volume of data, both in terms of the different dimensions that we can explore it across, and in terms of the timeliness of that data? And then do we have the right tools to then to hone in and to scope things down and understand where we're at, whether that's through context, critical path, these other tools that I talked about. The things I wanted to leave everyone, first of all, there's no magic. If it feels like your system is magical, that probably means that you just don't have the right tools yet. And that in particular, just having logging, metrics, and tracing aren't enough. Like, they're probably necessary in some way, but they're necessary as data sources, not as tools. The right tools will actually help you do better measurements and help you refine things. And those tools are hard to build, but fun. And so if you're excited about that thing, definitely come talk to me. And with that, I wanted to thank everybody for your attention, and if you have any questions, I'd be happy to answer them.
Any thoughts on using observability as a way to choose between designs?
Interesting. As in, we should design in this way because it will be more observable? I think that was sort of a bit of what the folks at Twitter were thinking about, that they should be able to understand sort of the components in isolation, and I guess in the same way that we might hold sort of globally the whole application to a particular level of service, that that's something that we can do for the individual components as well. I think, I guess I think of it more in terms of like what are the failure modes and things like that, but definitely being able to measure stuff is pretty important, and I guess being able to measure it, whether it's, I guess designing in such a way that we can test it under some artificial load and be able to say things about it in that case, or that we can actually test it in production in some way, and be able to, by test it I mean get the data out that we need even while it's in production. So I think if you look at Google, for example, the way that tracing and monitoring is done there is that's done live, like on every time you do a Google web search like that hits the tracing system, because they couldn't figure out a way to like load test at the scale of, or didn't find a way to load test at a scale that the real world has in a way that was sort of meaningful, and so that meant that they just had to be able to gather the right data from the production system itself.
I have two related questions. The first one is, who are the target users of this tool? You mentioned like 0 to 1 people at the company have expertise of figuring it out, looking at the logs, the initial logs. I guess the second question is, how generalizable is this tool that allows you to customize for different companies and reuse certain infrastructures?
Yes, I mean the target, I guess what, I mean, in a way, it's like this kind of tool, whether it's the one that we're building now or the one that Google built or whatever, anytime you're building a complicated system, where I guess, like, I mean, kind of looking back, you know, if you can describe the behavior of a system and with like a normal distribution, then like there's really simple tools out there that you can use to do that. But if the behavior of your system actually comes from the sort of aggregate interdependent behavior of these other systems, then I think you're going to need something that allows you to dig in and sort of see it from these different perspectives. In terms of generalizable, so what Google had built was pretty feature poor in a lot of ways because it had to operate at the scale that Google operates at. So because it was part of the online serving system, and at the time anyway, I think Google's published number was something like 2 billion requests per second. It had to be pretty simple. So there's a part of that which doesn't really generalize in the sense that like most businesses and organizations are not operating at that scale. But there's parts of it I think that are pretty relevant to smaller businesses. I think what happens is as you scale down a bit, you actually get the opportunity to add more features to it. Some of the things I described would actually be pretty hard to do in Dapper because of the techniques that they use around sampling, and that they need to do sampling in a very simple, low cost, and totally uncoordinated way. But if you're able to think a little bit harder, I mean, compute a little bit harder, if you have the time to do that, then you can start to do some of the things that I talked about.
Some more questions?
Cool. All right. Well, thanks, everybody.